here. So number 2 today for this mean value theorem on this packet, right? The question still stands, right? Can I apply the mean value theorem here? So in order for me to answer that question, right, does the mean value theorem work? There's 2 things you got to check off. What's the first thing? Is it
differentiable?
Continuous.
And is it differentiable?
I can't spell continuous. Continuous.
I'm good.
Why does that look wrong? Is it continuous? Second thing is,
That's right.
I'm going to take a picture of it just in case and then show my target.
is it differentiable?
That's wrong.
Wait, I wasn't done yet. Hold on. There.
Still wrong.
Is it differentiable?
Just kidding.
All right. So those are the 2 things we got to
Is
check.
it an R or a
Where are we pointing?
S or a?
It's an
Here? That's an
Yeah.
I.
That's not even pointing to it.
All right. Differentiable. How's that?
Okay, move on.
So-
you're still recording that?
What?
You're still recording?
Yeah.
Oh.
So just in case. So
You got called a dinosaur on tape.
so if you look at this function, what's the function we're looking at here?
1 over x minus 1.
1 over x minus 1 is a rational function. Yes? Rational functions have some issues at certain spots, right? Whenever you think of fractions, right, there should always be one particular value for a fraction that gives you some type of unease. Do you know what that value is? 0. Now 0 in the top of a fraction is perfectly fine. 0 over 5, that's just 0. 0 over 100, that's just 0. 0 over a billion, that's just 0. But if you have 0 in the denominator,
That's an issue.
that's an issue. That's where the function's undefined. And not only is it undefined for them, if you think to your past, rational functions, when you have that undefined moment, what happens at that function at that point?
Is there an open circle?
No.
Horizontal asymptote.
You got asymptote, right?
Vertical asymptote.
Vertical asymptote. It is a infinite discontinuity. Now, my question is, on this particular problem, where does that vertical asymptote occur? How do we figure that out?
Isn't it set the denominator to equal to 0?
Yeah, we're going to have a vertical asymptote, right, when x minus 1 is equal to 0, right? The reason for that is we'll end up with 1 over 0, which is undefined, right? That's not okay. So that happens when the bottom is equal to 0. That happens when x minus 1 is equal to 0. And we solve for that. What x value is going to cause us to have a 0 in the denominator? Solve for x for me. X minus 1 equals to 0.
1.
Add 1 to both sides, and you end up with x equaling to 1, and you're going to have a what? A vertical asymptote happens at x equals to 1. So, is this function continuous
No.
on the interval from 0 to 3?
Yes.
No.
No.
This is
But
asymptote. According to Desmos, it is.
No, according to Desmos it isn't.
Oh.
Yeah. Because what's the value we're looking at? X equals 1. That is between 0 and 3, right? And that gives us a undefined value, or in other words, a vertical asymptote. So it is not continuous. Not continuous. Since it's not continuous, I don't even need to check if it's differentiable, right? It needs to have both. So since it's not continuous, I don't even need to check if it's differentiable.
It's not different.
Yeah, it's also not differentiable.
apply.
Yeah. So the mean value theorem does not apply. What's up?
I want like the whole like.
Yeah, that's
Oh, I
fine.
think they didn't
What do I
know
think
that.
you're saying? Mean. Like mean value.
Yeah, mean value thing.
Mean?
Mean.
I know, but I still think mean. Like
Right here. It's this word right here. Mean.
Mean.
Yeah, no, mean. You're thinking of meme.
I'm mean.
That's pronounced Mimi. This is mean. Mimi.
Same thing.
And that's in the
I'm
Alright.
talking about the mean value. Like.
So, not continuous, right? I don't need to check the other one. So, the mean value theorem does not apply. So I cannot guarantee that there is a tangent that is parallel to it. Anita, what's up?
Why did you compare the vertical asymptote to the interval? It's not.
So that's the hard part about this, is trying to figure out when is a function continuous, right? I think that's what Esther asked. Like, how do you even start? How can you tell when is a function continuous or not? That's the whole That was the whole thing of chapter 1 if you think about when we first learned limits. How do you determine if it's continuous or not? I'll be honest with you. I kind of just faked it my way through on this whole thing when I was learning it. Basically what I would do is I either would graph it on Desmos. Well, I didn't have Desmos back then, but I graphed it on my calculator to see, like, is there anything weird that happens, right? And if there isn't anything weird that happens, usually it's continuous. The advanced way you're supposed to do this is you're supposed to have a knowledge of functions. Like, for example, if my function was sine of x, I know that sine is a continuous function. There's no issues with sine. But if it was 1 over sine, anytime sine is equal to 0, I'm going to have an asymptote. And asymptotes are functions that are, it is a discontinuity. It's not continuous at those asymptotes, right? So if you want like a quick checklist to see if something's continuous or not, I can give you 3 quick ones that are easy to check if the function even exists at those lengths. So rational functions are one of them. If you have a function where it's like a function on top of another function, in this case it's 1 over x minus 1, and you're looking to see if it's continuous or not, usually discontinuities for rational functions I can't spell right now. Rational functions have discontinuities. Yeah, this is scribble so people can't see my misspellings. Discontinuities occur when the denominator is equal to 0, right? So g of x cannot equal to 0, right? So then I would just try to find out when does this bottom part equal to 0, and that would be where my discontinuities occur. Does that make sense?
Yeah, I understand that, but I mean, like, because it's a vertical asymptote, it's not going to be continuous. So then why did you compare it to the
Oh,
interval?
mean value theorem doesn't look for the entire function. It only looks on a specific interval, right? The mean value theorem only proves something to be true if you're comparing it on a closed interval. Excuse me, here we go. So we're only looking on the interval that they tell us to look at it on. So for this particular problem, they tell us to look at it from 0 to 3 only. I only look from x equals 0 to x equals 3. That's the...
Well, like, why look if it's a vertical asymptote?
Huh?
But why do you have to look if it's a vertical asymptote? Like, we already know it's not continuous.
Well, we just found out it's not continuous because we just found out that the vertical asymptote is there. So that actually leads us to number 3. Check out number 3. What's the interval they're asking us to look on? 0 to 3, right? Same thing applies, right? We're trying to see if the mean value theorem applies here, right? 2 things you got to check off. Is it continuous? Is it differentiable? Yeah? So, same thing as before. I'm looking at this thing. It is a rational function. Rational functions have issues when the denominator equals to what?
0.
So, when does this rational function have a 0 in the denominator?
-1.
X equals to -1. So, this function is not continuous at x equals to -1, right? This right here is a infinite discontinuity. But Stephen's already mentioning it, right? Yeah, x equals to -1 is not between 0 and 3. Do you see that? I'm not focusing on the function at x equals to -1. I'm focusing on the function between 0 and 3. And if this is the only place that causes a discontinuity, this function is continuous on the interval 0 to 3. There's no holes, there's no asymptotes. The asymptote only occurs where? Off of the interval. So it is continuous. So the first thing checks off. It is continuous from 0 to 3. The next thing you need to check is if it's differentiable from 0 to 3. But it's on the open interval. So we don't check the endpoints themselves if it's differentiable, but we check everything between it. Now, easy way to check differentiability, right? First things first, make sure it's continuous, right? And it is. We just said that it is from 0 to 3. It is continuous. The second thing you need to check is, are there any corners or cusps? Now, corners and cusps, I can't not say it. Corners and cusps only happen 2 times, right? Corners occur at absolute values. This problem has no absolute values, so there's not going to be any corners in there. Cusps happen at usually a square root. Is it a square root? No. No. Yeah, I'm sorry. Usually a root and something being squared. That's usually how cusps occur. Don't laugh at my speech impediment, please. So this function has none of those. It doesn't have a cube root and a squared in there. It doesn't have an absolute value, so there's no corners. And it's also continuous on there, so it's going to be differentiable as well. So these two check off. So can I apply the mean value theorem to this? Yes. The mean value theorem applies. Which means what? Yeah, there's a derivative, right, for some value of c such that it's going to equal to what? H of 3 minus h of 0 over 3 minus 0. In other words, there's a derivative that's equal to the slope of the secant lines. That's it. Okay? That's it for that one. So we can actually solve it, but for right now I'm just showing you, right? We're just proving it exists. That's the main part, right? Proving that it does exist at some point. Okay? That's the mean value theorem in a nutshell. It's this idea that there is a value that exists. Now, the algebra part of it is solving it, like taking the derivative, setting it equal to what that slope is, and then solving it algebraically. We'll do a couple of that today, a couple of those problems today. So then that way you can be set up and ready to do the homework. But for right now, understand the mean value theorem is simply just a theorem that proves its existence. That's all. It proves it exists. Now, if you're still struggling to see if it's continuous or differentiable, you could do what I did and just kind of fake it along the way and graph it. Honestly, graphing it is a nice tool for you to learn until you get used to seeing, like, can you tell it's continuous? Can you tell it's differentiable? So let's say you graph this one, like number 2, for example. Let's go graph this one right here, 1 over x minus 1. Let's go graph that and see what that looks like. Okay, so let me open up this right here, bring it over there, open that over there. So let's go to Desmos, my favorite app. And what was the function? 1 over x minus 1. Okay? Check it out. If you can't tell that this is not continuous at all the points, I don't know what to tell you, right? Like, picture, can you draw it without picking up your pencil? That's usually the easiest way to talk about continuity. Since it jumps right around here as it goes down towards negative infinity over here, and then it comes back from infinity over here, I can tell that it's not continuous, right? And then we did the algebra work to see where it was not continuous at. We saw it was at x equals to 1. Can you see it? Make it a little bit nicer if you draw in the little, my favorite was it? What do you guys, my dashed line right there. You see it? Easy to see, right? X equals to 1 being our discontinuity happens to be on our interval, so I can't apply the mean value theorem. That's it. All right. Actually, here we go. I did end up finding one of the things I did earlier in my other classes. Ignore all of this. Ignore that. Ignore that. Ignore, no, we need that. So look back at number 1 real quick on your notes. Number 1 that we did on Thursday. What was the function? 4x to the power of 3. What else we got? Minus x squared plus 4. Okay, check this out. It was between -1 and what? There we go. So you see the graph that I have drawn there? The red line is the function itself. 4x cubed minus x squared plus 4. Yeah? Beautiful graph, yeah? But I'm only focusing on this graph between -1 and 1, right? Check this out. When we did that problem, when we did that problem, did the mean value theorem apply? It was continuous and it was differentiable, right? That means that there should be a tangent line that's parallel to the secant line. Do you see the secant line, by the way? What color is my secant line on my graph right here? What color is that secant line on the board?
I mean green.
It's green. Do you see the secant line? The red line's the function, the green line's the secant line. Yeah? What I'm saying is that there is a tangent line that is parallel that needs to exist. Can you picture it? In fact, we were able to solve this last time. How many did we find, by the way? Do you remember? Let's go back at our notes.
2.
We found 2. So we proved that the mean value theorem applied, right? Because it was differentiable and it was continuous. We found out that the slope of the secant line was what? Slope of the secant line is 4. And then I just solved, right? When does the derivative equal to 4? And we did this, so we came out to a nice, what do we call this? Started with a Q. It was a quadratic equation, right? You could have solved it using the quadratic formula. We solved it by factoring. What are my 2 answers? X equals to negative 1 over 2, and x equals to 2 over 3. Go back and look at this graph real quick. Well, I already forgot the numbers. What was it? Negative 1/2? Look at where negative 1/2 is. Negative 1/2 is, why am I having trouble here? Negative 1/2 is point what? 0.5. Bro, can you like, there you go. So at that point right there, if I were to draw a tangent line, it should be parallel to the green line. Man, okay, let's see if I can actually do this correctly. So, bear with me real quick. I struggle with this a lot. So, let's see here. I'm going to say I'm looking at y minus f of negative, was it 1/2, right? 0.5?
Yeah.
Good. Is equal to 4 times x minus plus 0.5 is that point if we do that. Luckily, we've been practicing our slope formula. Do you see it?
Mm-hmm.
See the red line that I drew?
Yep.
Isn't that nice? It's a tangent line. Is it parallel to the green line?
Yes, sir.
Yeah, because the slope I typed in was 4, right? You see that? Boom. And notice that the slope calculation I have right here, I did try to program that earlier. What do you notice? It's 4. So that's one parallel line. Where's the other parallel line happening at? What was the number? Whoops, that's the wrong thing I want to open up. It was positive or negative? Positive 2 over 3. So let's go ahead and put that in there as well. Let's put that same equation. Y minus f of 2 over 3. Knock me. Stop it, panicking. Stop panicking. Equals to 4 times x minus 2 over 3. Knock me. Get it together. Do you see the 2 parallel lines?
Yes, sir.
That's exactly what we solved. That's all we were doing. We're just solving for where they occur. And you can visually see that they exist. Now again, the mean value theorem doesn't help you find both of them. It guarantees that there exists what? At least one. And that's the main purpose of the mean value theorem, is to prove that it exists. We have to do the work to find out where they occur. Does that make sense? So anyways, that's a long spiel about all this here, but I just wanted to show you, right? If we looked at, for example, 1 over x minus 1, and I take these lines off here, we don't need you anymore. Let's get rid of you, and just look at that function. 1 over, what was it? X minus 1. And I was looking from it from 0. What was it? 0 to what?
3.
Let's zoom out a little bit and take a look at that function. Can you see it? If I were to pick up a ruler, how convenient, and I looked for the tangent lines here. So if I follow the red line here and I follow this tangent line like this, you see how none of these are going to be parallel to that green line?
Yeah.
So none of these over here are parallel to it. Come over here, do the same thing. Tangent line, tangent line, tangent line, tangent line, tangent line. And up to this point down here, none of them get parallel to that green line. And it matches because the function is not continuous. It doesn't exist. There's no way I can get this green line to match up with any of the tangent lines. Does that make sense? Now check this out. The other one was x what? x plus 1.
That's the one I was looking at.
Yeah. Now, on this one, on the interval that we're looking at from 0 to 3, does it look continuous?
Yeah.
Yeah. Is it differentiable? Yeah, there's no corners, there's no cusps, right? So, there's a parallel line on there, and we can actually figure that out. And that's what I want to do today for number 3. Let's actually do a little bit of algebra and solve to see if we can find out where between 0 and 3 does that exist. Now, the mean value theorem proves that it exists. Now we're just going to do some algebra to find out where it exists, okay? Let's do that real quick. You guys number 3? You have enough space for this? If not, you might want to do this on the back. Whew. We're going to do number 3, and we're actually going to apply the mean value theorem and find that missing spot. So first things first, once you've proven that you can apply the mean value theorem, meaning you've checked off that it's continuous and that it's differentiable, and the mean value theorem applies, I suggest the next thing you do is to find the slope of the secant line, this part right here. So let's find the slope of the secant line. I'm going to abbreviate this. The slope is lowercase usually, right? Slope of the secant line, which is equal to h of 3 minus h of 0 over 3 minus 0. What was the function though? H is what? 1 over x plus 1. So let's do that real quick. What's h of 3 equal to? 1 over 3 plus 1, right? Minus 1 over 0 plus 1 all over 3 minus 0. And I'm going to see what the heck does this equal to. Man, don't you guys just love fractions?
No.
Don't you guys just love fractions? Aren't they nice?
Yeah.
I don't believe you. Well, how about this? 1 over 3 plus 1, that's just 1 over what? 4 minus 1 all over 3. What's 1 over 4 minus 1? Or negative 3 over 4 over 3. You have a fraction over a fraction, negative 3 over 4 over 3. We'll simplify one more time. You ready? Or negative 1 over 4. So what's the slope of the secant line? Or negative 0.25 if you want to keep in decimals, right? Which kind of makes sense, right? Which kind of makes sense. I see you guys writing right now, but if I were to put back the Desmos graph, did it look like it was a negative slope? Was it going down from left to right?
Yeah.
Was it very steep? No. It was actually closer to 0 if you looked at it. Look. Is that steep? Is that a steep line? That green line? Not very steep at all. And it kind of makes sense because when we calculate the slope, it's actually a fraction that's less than 1. So it's not a 45-degree angle, right? It's just like a nice little line right there. So we found the slope of the secant line, and I'm saying I need to find out when is the derivative equal to that. So if my function, h of x, is equal to 1 over x plus 1, I need to find out what h prime of x is. So, what? You can. I don't know if you heard that. Steven's saying we could do low d high minus high d low over low low. That's one way to do this derivative. Is there another way?
Yeah, you can break it apart.
Yeah, what do you say?
Like you can break the fraction apart.
No, we can't break that fraction apart. If the plus was in the top, we could. If it was x plus 1 over 1, you could split it. But since in the denominator, we can't split the denominator, right? Denominator stays the same when we add fractions. But you have the right idea. We should rewrite it, yeah? Would you not agree that you could also write this as x plus 1 to the negative 1 power? And then you could use the chain rule. Chain rule works as well. Derivative of the inside times the derivative of the outside. Whichever method you want to do. So right now, can you guys take a minute right now and practice your derivatives right now? If you want to use the the quotient rule, you can use the quotient rule. The high is 1 and the low is what? X plus 1. So you can do low d high minus high d low over low low. You can do the chain rule as well. But I honestly suggest, I know all of last chapter I told you, don't simplify, don't simplify. You don't have to simplify here either. But just keep in mind, when you find out what h prime of x is, when you find out what the derivative is, what are you going to set it equal to?
Oh.
What am I going to set it equal to? Not 0.
The slope?
Yeah, the slope. What is the slope? Yeah, so it's up to you how simplified you want it to be, because you are going to have to solve it. Yeah. So take the derivative real quick. Let's do that real fast. Let's practice the quotient rule or practice your chain rule. Either way, do the derivative of that right there, the 1 over x plus 1. Okay? I'll put it off on the side while you're doing that. You don't have to look up, but practice, 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 right? You can do the quotient rule.
See, practice? Yeah, I did multiply, like for the second one.
All right. Check your answers with what I have. Does that make sense? Does it not make sense?
Oh yeah, that makes sense. Oh, I didn't like simplify even more after the quotient rule.
So, if you're doing the chain rule, which I prefer, the original function, if you rewrite it into this, x plus 1 to the negative 1 power, yes? If you're going to chain rule, you have to do the inner function. And the inner function is x plus 1. Its derivative is just 1, right? And the outer function is some stuff to the negative 1 power. Its derivative is to do the power rule. Bring down the negative 1, leave the stuff that's inside, and then we just you subtract. You subtract. Yeah, so negative 1 minus negative 1 will give me negative 2. Yeah, so power rule along with the chain rule to give me that negative 2 there. Okay? Either way, it comes out to this lovely derivative right here, negative 1 over x plus 1 quantity squared. Yeah?
Oh.
So, knowing that it exists, if I was asked to find out where it exists, I simply take this derivative of negative 1 over x plus 1 squared and set it equal to negative 1 over 4. How good are you at solving equations? This is a algebra 2 skill, or in other words, an IM 3 skill. Do you remember how to solve
You
rationals?
do that grade 9.
Yeah, I did it either.
So let me give you some tips and pointers, right? If you have a negative sign on both sides, you can just write it as positive, right? The negatives cancel each other out. So I don't like dealing with negatives, and usually I just cancel them out if I see them on both sides, right? So I would write this as 1 over x plus 1 squared is equal to 1 over 4. You can cross multiply if you don't like fractions. That's one of the best techniques I've ever learned when I'm dealing with fractions, is to just not deal with them. I'm not even making it as a joke. If you ever have fractions, you're like, I don't want to deal with fractions. Multiply by a common denominator, and it will cancel out all your fractions, and you'll just have a nice polynomial. Now, there's a slight like issue with that, just a small one, and it's very rare. But do you remember where is this function not defined? At -1. So if I do that and I work out my answer, and one of my answers come out to be x is equal to -1, I can't say that's an answer because it's undefined there. So just keep that in mind. The trick that I just told you, multiply, cross multiply, which is what I'm going to do right here. You ready? Cross multiply x plus 1 to the top right, so it'll be x plus 1 squared, and then cross multiply the 4 over to the other side. There's one slight issue. You got to make sure that when you do this, you understand domains, right? So this is 4 is equal to x plus 1 squared. I have to understand that at some point, x cannot equal to -1. Just keep that off on the side somewhere. Just know that, yo, I just cross multiplied by this. I got to keep track that that's a number that I can't have as my answer. Chances are it won't come up as one of your answers. That's really rare, but if it does, you know, you can screw yourself over and just be like, ha, the answer is -1. But it's not. Anyways, let's solve this problem. Isn't this a little bit easier to solve? 4 is equal to x plus 1 quantity squared. How do you solve this?
You distribute the square first.
Ooh, okay. We could do that.
Just do x plus 1, x plus 1.
You could do that, yeah.
And then you'll do the -1 on both sides.
Wait a second. We can't do just -1.
Oh, shoot.
You got to distribute first, right?
You know what?
So-
I'll drop this class.
No. Well, actually, you might even angrier after
Look at
this.
my sister.
So, help me out here.
They can't.
What can I do to solve this problem?
You can factor. Like,
That's already
Wanna
factored?
factor it.
You mean distribute?
yeah, that.
X squared plus 2x plus 1 is equal to 4. How do you solve this quadratic?
You have to subtract
By what?
by
4. Subtract by 4, because if it's a quadratic, you want to set it equal to what if you're solving it?
0.
So, 0 is equal to x squared plus 2x minus 4. 1 minus 4 is what?
That's 3.
-3.
-3.
Do you want to use the quadratic formula, or do you want to factor?
Ah, hell.
X factor.
So, factor it real quick. We get 0 is equal to, factor it. X and x is the only way to make x squared. What numbers multiply to 3?
-3 and 1.
1 and 2.
1 and 2 do not make. 1 and 2 does add up to 3. I'm saying multiply. Factors that multiply to 3.
So 3 -1.
Positive 3, -1. What are my two answers? X
You only
plus
have one
3
negative.
equals 0.
We got 2 answers. Never mind, because when you set it equal to 0, it's positive.
Yeah, so we got x equals to -3 as one answer, x equals to 1 as the other answer, but only one of them apply for this problem. What's my interval for this problem? It's from 0 to 3. Remember that? The interval is from 0 to 3. So which one of these is the answer that's between the interval from 0 to 3? The only one that works is
1.
So this does have a line that's parallel, by the way, if we were to look at the graph. At -3. Do you see at -3, that's all the way over here. Can you picture that tangent line right here? Does it look like it's parallel to the green line?
No.
Can you see it? Just pretend, right, that there's a line drawn there. It is parallel, but it's not on the interval that we care about. The interval that we care about is at x equals what? Right there. Come on, bro. Come on, bro. Just there. So that would be parallel to that green line, and we found it, right? This takes a little bit of algebra skills, yeah?
Yeah.
Did you know there's another way to solve this algebraically besides what you just did, which was to distribute? This is not wrong, by the way. You can do this. You get your answers. You know there's an easier way? You can square root it.
I figured.
Square root both sides, and you'll actually end up with this. You ready? Plus or minus 2 is equal to x plus 1. Why is there a plus or minus?
Because that's just how it is.
Because you square rooted a variable. That's the part that people tend to forget. The square root of 4 is just 2. But if you have a equation with an x squared, you have to include a plus or minus. But yeah, you can just do it here. And then subtract the 1 to the other side. You'll have negative 1 plus or minus 2 is equal to x. Negative 1 plus 2 is 1. Negative 1 minus 2, negative 3. That's why there's two answers. But you only care about which one? That's where the tangent line that's parallel to the secant line exists at. Neat? Not neat? Kind of neat?
Very neat.
Very neat?
We're saying, do they meet?
Is it neat?
Neat.
Oh, I heard meet.
All right. Another thing I wanted to share with you is your homework. I posted it over the weekend, but I didn't think any of you would really check because it's over the weekend.
I did. I saw it.
Oh.
I just saw it.
It-
I only check my college.
It's also not due today, right? It's not due today. It's due. Let me see.
I
Yeah.
saw it, turn on the
Let's see here.
Didn't finish.
So by the way, the first thing, the mean value theorem worksheet is just this notes. You finished these notes already, right? Just take a picture of the last page for me.
This one?
Yep. And submit that for me. This is just in your notes.
Both are back because we did it back.
Yeah, if you did
Why?
2 pages. Because. Submit it for me to show me that you've done these notes.
Oh.
Second part is your actual homework. I've posted it. There's 2 pages on there. But not that bad, right? It's only like, what, 7 problems on the first page and then 8 problems on the second page. But check this out. I wanted to go over 1 problem with you, so it'll be 1 less problem for you to do. So, the first page is this thing called the extreme value theorem. We're going to talk about that later, so don't worry about that just yet, right? So we'll talk about that a little bit later. But on the second set, which is down here on page 208, I want you to do numbers 6 through 48, multiples of 6. Check this out. These all have to deal with the mean value theorem, and they want you to find the value. So not only do you have to prove the existence of it, that's part A. Part B is proving or finding out where it does exist, if you can prove it. So I know some of you said you were struggling with figuring out if it's continuous or not on a function. So let's do a function together, right? Let's do one of these together. Let's do number 6 together, right? What's the next number after 6?
8.
That's multiple of 6.
Oh.
12. So 12 will be the next one. So let's do those 2 problems today, and then you'll have 2 less problems to do on your homework. Right? I'm just too nice. I'm just so nice, aren't I? So I'm going to go over to here, and let's start up on a new page here. Let's call this 4.2 homework.
Put a W at the end.
Help. Put a W at the end?
Yeah.
Why?
W.
I'm just going to press enter and ignore that you said that. And here's the problem that we're looking at. The function is ln of x minus 1 on the interval from 2 to 4. Ln of x is another function that, by the way, that you need to understand that its domain is that a thumbs up, thumbs down?
Oh, it's for
This- That's pretty cool.
for
Did-
discussion.
Did she print it out for you?
I have no idea.
I don't know.
She gave it to us. She just gave it to us.
She made that for you?
Yeah.
That's amazing.
Well, I mean, I'm pretty sure we have to give them back, but you know. They have hearts on them. They're cute.
That's adorable.
Oh, maybe she bought them. I don't know.
Oh,
Still a lot
that's
of work.
still cool. I would never do that.
She wouldn't.
No. Wait. Yeah, I'm just gonna accept that. Okay, so the homework states, right? Part A. State whether or not the function satisfies the hypothesis for the mean value theorem. If it does, for part B, we're gonna find where it's parallel. So let's go ahead and first things first. Part A. can I apply the mean value theorem? What are the two things you got to check off for the mean value theorem to work? Continuous, undifferentiable. I don't know, you said it that way, so I'm just going to go with it. So those are the two things we've got to check off, right? Is this function continuous on the interval from 2 to 4? Do any of you remember any issues with natural log?
Yes, I didn't understand.
So if you don't, it's okay. It's one of those things, it's like it kind of gets brushed over. You're just kind of like, natural log is this function, and I don't know if you remember it, the natural log function is basically something that looks like this. And if not, that's okay as well. Natural log is the inverse function of e to the x, if you want to think of it that way. E to the x function is a continuous function, right? And it has no issues. Natural log has an issue, just a slight one. Look at this right here. It will never reach the y-axis. The thing inside natural log can never be 0. And if you go to your calculator and typed in natural log of 0, check this out. If you turn on my calculator. Hello? I'm pressing.
It looks like you just take a picture and post it.
There we go, there we go, there we go. So what I'm saying is this. If I took the natural log and I typed in 0, check out what happens.
Error.
It's an error. Not only is it an error, what type of error is it?
Wait.
Domain. 0 is not in the domain of natural log, right? So you can't have 0 in there. You also can't have negative in there. But you can have things that are very, very close to 0. So if I were to look at, let's say, not 0, but at 0.1 per se, I will get an answer, right? So natural logs is one of those things you just kind of have to know where your issues are. Like I said, earlier we talked about fractions, right? You know by heart, fractions can't have a 0 in the denominator. I'm letting you know right now, domains of logs are another one. And the inside of your log, whether it be natural log or log base 10, can't have a 0 or a negative. Can't have a 0 or a negative. So this thing will break if I have a 0 in here, if this is equal to 0 or it even equals to anything that's negative, right? So for example, if x was equal to -1, I'd have -1 minus 1, which would be -2. The natural log of -2 is undefined, right? So -1's not on here anyway, so I don't have to worry about that, right? But what I do have to worry about is, when does this thing equal to 0? So help me out here. When does x minus 1 equal to 0? When x is what? 1.
But it's not in the interval.
Is 1 in the interval?
No.
1 is not in the interval, so we're safe, right? So this function does exist between 2 and 4. Not only does it exist, it's continuous from 2 to 4. It's not continuous at 1, right? But it's not on an interval, we don't care. But it is continuous on the interval 2 to 4, so I put a little check mark. It works. Okay? Second thing, is it differentiable? Remember, when is differentiability a problem? When it's not continuous, when it has a corner, or a cusp. Corners happen at absolute values. Do we have an absolute value here? No. Cusps happen at radicals with x squares. Do we have that here?
No.
So question, so it's continuous, right? So why is the x, like why doesn't the x equal 1? Right there.
If x equals to 1, we would have the natural log of 1 minus 1, which is the natural log of 0, which is undefined. Now, everywhere else, though, it's continuous, right? Well, there's some parts where it's not, but I'll show you right there in a second. But right now, from 2 to 4, because that's the interval we care about, it is differentiable as well. Now again, if you're like me and you struggled with this, which I struggled very harshly on whether or not to find out if the function is continuous or differentiable, practice graphing it, right? I know on the AP exam there's be a section where you don't have a graphing calculator, but for now, just use that tool to help you, right? So let's graph natural log of x minus 1 and just see what it looks like, okay? So let's go ahead and graph that real quick. So instead of 1 over x plus 1, let's type in the natural log of x, crud, was it plus 1? Minus 1. How's that graph look?
Red.
It's continuous, isn't it? But look at where the vertical asymptote is occurring at. What's that value? At 1, at x equals 1. You see that? It just shoots straight down. Not only does it shoot straight down, there's nothing else on the left side. You see this function doesn't exist anywhere over here. Natural logs do that. They don't have both sides of it. Once you find that asymptote, it just stops there. Right? So it doesn't go past that. So the function is continuous. Do I see any corners? No, I just see a curve, right? So it's differentiable. By the way, I'm not looking at it from 0 to 3. I'm looking at it from 2 to 4. Yes. Now looking at it from 2 to 4, clearly continuous and what? So can I apply the mean value theorem? Yeah. And some of you can already see it exists, doesn't it? So let's go ahead and do that part A. We're done with part A. You ready? Continuous and differentiable part A. Mean value theorem applies. That's all part A is asking for. Oh my God. We're not going to talk about the fact I just hesitated on how to spell applies. But yes, it applies. The thing is, the thing is, I hesitated and I didn't even know what I was confused that it would be besides LIES. I was like, what's the other option? Knock me?
It's lies.
Yeah.
Get it?
Full of lies.
Get it because it's L-I-E-S.
Okay.
You didn't major in English, you majored in math.
Yes, that's true. And
Thank God for that.
there's a lot of
No,
lot of English
like,
involved.
No, because if you were majored in English and you would have been making mistakes like that, then you probably would have a hard time finding a job.
All right. So part B says if it does, find the value of c on the interval that satisfies the equation. So part B, we got to do two things. We got to find out this part right here. We're looking for f prime of x such that it equals to the slope of the secant line. Excuse me. Ah. Dehydration. Hold on. Let me raise that. So this will be f of b minus f of a over b minus a. Right? So I need to find the slope of that secant line. Oh, this is going to be a calculator problem for sure. You ready?
You go to Disneyland a lot?
No. Well, last year I went 3 times, but that's because they had that pass,
Oh, yeah.
the SoCal pass.
Yeah.
I haven't been
They
to
still have
Disneyland.
that though, don't they?
Probably, but I'm not going again for any time soon.
I haven't
I've
been.
You got
had
tired
enough.
of it?
I finally got I got to go on the new ride, the Rise of the Resistance, or
My friend is a Disney adult. He's 25 and he goes to Disneyland. I
My
kid you not. Every day. I kid you not. Every single day.
That's my
He
sister
literally
is
goes to a
28.
specific ride and makes sure that he's always the high schooler every day.
the Buzz Lightyear ride,
I don't remember.
or the
Well, the
Toy
Buzz
Story
Lightyear
ride.
ride was so stressful for me. That's how I went. It's too much.
All right, what was we? Okay, so before we start talking about random stuff, my A and my B is right here. A is 2, B is 4, right? So if I'm looking for the, let's do this real quick on the side over here. Let's say I was looking for the slope of the secant line, right? I'm going to plug in f of 4 minus f of 2 over 4 minus 2. Well, f of 4 is equal to the natural log of 4 minus 1 minus f of 2, which is the natural log of 2 minus 1. This is all over what? 4 minus 2, which is just 2. So this, by the way, is the slope of the secant line. The green line on the graph that I was having drawn, right? This green line right here, the slope of this green line. I have the answer right here, by the way. The slope of that green line is this weird decimal down here. But we'll do it by hand, just to, I lied. We will do this by calculator. Because, check this out. ln of 4 minus 1 is just ln of 3, right? Minus 2 minus 1 is going to be ln of 1 all over 2. Do you know what the ln of 1 is equal to? It's okay. Ln of 1 is equal to 0.
Yeah.
Not everybody knows that.
Why does it look like a gel pen and the red always looks like a gel pen and
how does the purple look?
Looks like purple.
What about the blue?
That one looks normal. It's just the red one. And the purple one kind of. It has like a little shadow to it.
Well, I don't know. I did not code it, so
Okay, let's
it
continue.
is what it is. So the slope of the secant line needs to equal to ln of 3 over 2, which is a really not nice number. I'm going to just leave it as ln of 3 over 2, but if you really wanted to, you could type it in as ln of 3 divided by 2. It's going to give you this decimal right here. 0.5493, blah, 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 blah. All right, that's the first part, slope of the secant line. Second part, I need to find the derivative. Well, I have this function, ln of x minus 1. Do you know what the derivative of ln is? Do you remember it?
Is it 1 over?
Stuff. So ln of x would be 1 over x. But this is ln of what? It's ln of x minus 1. So you have an inside and an outside function. The inside function is x minus 1. Derivative of x minus 1? X minus 1? Derivative of x? 1. Derivative of x is just 1. But the derivative of ln of stuff will be 1 over said stuff. So you chain rule this, and you'll get the derivative of the inside, which is 1, and the derivative of the outside, which is 1 over stuff. Ta-da! You okay? You not okay? You okay?
I'm alright.
Mentally or physically?
Both.
Physically, I'm dying, but
I have a
mentally,
lot of knee pain right now.
Oh, that's not good.
That's a
Have you tried popping it out and popping it back in?
Oh my god. Oh.
No, don't actually do that.
I've been eating McDonald's for the past 3 days.
That sounds amazing.
That sounds
No.
I'm gonna be honest, I have an addiction to McDonald's.
McDonald's is not good at
It's
all.
good.
All right.
They have McFlurries, but even those aren't good anymore.
Okay,
I
the
get
chicken
a,
nuggets, yes.
two
And the
spicy
ice
No,
cream.
sandwiches
the
and
chicken
a-
nuggets from Chick-fil-A are so much better than
Large
McDonald's.
too.
They are good, but
Chicken sandwiches are so good.
good.
No,
Alright.
not crispy, regular.
Bring it back, bring it back, bring it back. Focus, focus.
I don't like crispy.
So, I found the derivative. I found the slope of the secant line. I'm just going to set them equal to each other and find out what does x have to equal to for this to be equal to that. Now, solving this algebraically is a little bit of a pain, but luckily I've shown you guys how to deal with fractions, right? You guys don't like dealing with fractions? Well, I can get rid of some of the fractions. I can cross multiply things, or I can just flip this, okay? You ready for this? My x is in the denominator. If I just cross multiply some stuff, check this out. I can rewrite this as x minus 1 is equal to 2 over ln of 3. I flipped it.
Wait, can you repeat that?
Say that, hold on, what'd you say?
What was the exponent?
There's no exponent.
Over the 3?
It's just under.
Because he flipped
Oh,
it. He
okay.
flipped it.
Yeah.
I get
So,
it.
so what if you're having trouble seeing this? I took this fraction and I kind of just flipped it.
Oh, okay.
And if you don't believe that that actually works, check this out. Would you agree that 2 over 10 is the same thing as 1 over 5?
Yeah.
Yeah.
Would you agree that that equals to each other?
Yeah. Oh yeah. Yeah.
Then at the same time, wouldn't you agree that 10 over 2 is the same thing as 5 over 1?
Yes.
Yeah.
That's what I did here. You see what I did there with the x's?
Yes, sir.
I just flipped that. So this is technically x over 1 minus 1. I'm sorry, x minus 1 over 1. Dyslexia is hard.
You actually have dyslexia?
A little bit. Now, check this out. Check this out, check this out. Remember what I said though, if you do this, you got to make sure that you remember what's the issue with fractions. You can't have a what in the denominator.
Zero.
So I got to write on the side as a note, hey, just a real quick note, x can't equal to 1. Because if x equals to 1, I'd get a 0 in the denominator, right? So put a note on the side that that part of the domain needs to be there. What's up?
Does the little slash always have to be on that side, or can I go the opposite direction?
Oh my god.
You can go the opposite direction. All right. You ready for me to solve this? Add the 1 over, I get x is equal to what? 2 over the natural log of 3 plus 1. Ta-da. It's done. If you want the decimal, you could plug it in the calculator and get the decimal, but I don't really care for the decimal. But if you really want it, 2 over the natural log of 3, that's going to give me this weird decimal. add 1 to it, and my answer is going to be at 2.82 and some decimal values.
I got the knock me mentality. I want to do all that.
Yeah, I'm actually, I prefer this more because that's the exact value. If you learned chemistry with Miss T, I believe she teaches things like the exact value and then there's like an estimated value, right? That bottom one is the estimated value. Rounded to only 2 decimal places though, not 3. Anita, you had a question?
Could you cross multiply?
You could. I don't want to deal with x minus 1 times ln of 3 though. But you can. You'll develop shortcuts for fractions the more you practice with them. My shortcut for this one is just to flip both of them. But honestly, it's one of those things like if you ever solved a problem where it was like 1 over x is equal to, 1 over x was equal to like 5 over 10, for example, you could cross multiply and write this as 10 is equal to 5x, right? But then you have to do what to both sides? Divide by what?
5.
Or, what you could have done was just do this and write it as x is equal to 10 over 5. You know what I mean? Like it's the same thing as cross multiplying and dividing, right? So you develop those little shortcuts here and there. Anyways, my answer is at about 2.82. Let's go look at the graph real quick. Where's 2.82 at? 2.82 is right about, what was the decimal? It's 2.8204. 2.820. 2.82. Right about there. Does it look like it's parallel at about that point, the tangent line? Yeah, let's go ahead and, oh man, I hope I can still do this. Y minus f of 2.82 is equal to,
You got this, now.
Jeez. 0.5493 times x minus 2.82. How's that look? Look parallel?
Enough.
Yeah, it's close enough.
Yeah.
It's good enough.
Yeah.
Good enough to pass.
Yeah.
Right? So, how's that feel?
It feels good in here. Out there, it doesn't.
So, concepts I really want you to grasp. How do you apply the mean value theorem? What are 2 things you need to look for?
Make sure it's continuous and differential.
If it is, does the mean value theorem apply?
Yes.
It does. That means there exists a tangent line that's parallel to the secant line, right? That's the calculus part. That's what I want you to be able to show me, that you prove its existence. Finding the value of it, that's just algebra. This whole thing from here to here, I don't really care. It's just one of those things that you have to kind of practice doing, because math. But for calculus' sake, all I really care about for this part is just understanding that you know how to use the mean value theorem. Does that make sense? Yeah? Okay.
So on the homework, if we just do that, so we get
You'll have part A done. I still want you to attempt part B, at least the setup, like this right here. Understanding that the derivative is equal to the slope of the, I'm sorry, it's this down here. That the derivative is equal to the slope of the secant line. At least set that up. You don't have to solve it, because again, that's just algebra work, but set it up to show that you understand that this occurs because the mean value theorem holds true. Does that make sense? You okay with that? Some problems are going to be a lot tougher than others. Let me go double check this real quick. Go back to here?
No, Gizmo
Desmos?
or Des. That other decimal, what's the decimal? Like what number is that?
Which decimal?
The 0.5. Where do you get that?
Oh, you remember our slope of our secant line?
Oh, okay.
That's what that decimal is.
You did that in your head?
No, the Desmos did it for me.
Oh, I was gonna say.
I
Not me. You're
I-
a genius.
No, I programmed Desmos to calculate it for me.
Okay.
So whenever I type in a function in here, it'll do f of b minus f of a over b minus a, which is right there. You see it, the equation?
that looks very cool.
Yeah, isn't it? I was programming this so that it would automatically draw the tangent line for me. And I found out that's really hard to do, so I just stopped. So now I just kind of like, I have to like draw it by hand. But it's okay. Anyways.
Would it, if it's like a certain level of difficulty to do the like automatically and then do it by hand, wouldn't it like add up to just do it a bunch of times by hand?
So the issues were, so this case works out because there's only one tangent line. The issue I came across is what happens if the function has two tangent lines? Will it know which one to display? Or will it be able to display both? That's the hard part I was trying to get to code. And I was like, forget it. Anyways, what I want to talk about was the next one, which is number 12 on your homework. Right? Look at number 12. Temperature change. It took 20 seconds for the temperature to rise from 0 degrees Fahrenheit to 212 degrees Fahrenheit when a thermometer was taken from a freezer and placed in boiling water. Explain why at some moment in the interval the mercury was rising at exactly, in that interval the mercury was rising at exactly 10.6 Fahrenheit per second. What the heck does it mean? So let's talk about it. What's the name of this section that we're in? What's it called? What? The section. What's the name of the section that we're in?
Temperature change.
Really? The section is called temperature change?
That's what it says in bold.
Yeah.
No, this unit that we're in.
Oh,
4.2.
You didn't tell us.
This is homework.
You didn't tell us about what the
Mean
introducing
value
the
theorem?
Mean value theorem. The mean value
I was
theorem.
waiting to see if anyone else would get it.
The mean value theorem. Yeah.
Oh, look at that, it's right there.
Mhm,
Very
mhm,
nice.
At the top of the
Yes,
paper.
I know. So anyways, so the section, its main focus is the mean value theorem, yeah? So, remember, what's the mean value theorem state? It states that something has to exist, right? Look at how the wording of this question is. It says to explain why, at some point, the temperature rising is rising exactly at 10.6 Fahrenheit per second. It's an existence. It's proving that that value should exist somewhere between the starting point and the end point. Yeah? Now, here's the thing. We've been dealing with x's and y's for our start points, right? The interval that we usually dealt with was some a to b. Yeah? So some start value to some end value, right? Well, in this problem, how long is the values going from?
20 seconds.
For 20 seconds. So what does the start time at? It's going from 0 seconds to what?
20.
So it's saying at some point between 0 seconds to 20 seconds, the rate at which the temperature is rising should be equal to,
10.6.
so here's my quirky little graph here, yeah? Let's say the time is down here, and I have the temperature up here. When it's at 0 seconds, how cold is the thermometer? What's it saying at? What's it starting at?
Oh.
What's it starting at? 0 seconds, 0 degrees what? At 20 seconds, what's the temperature now? 212.
212, sorry.
Oh wait, should we draw this graph?
I would. So at 20 seconds, it's 212 degrees Fahrenheit. So I have time and I have temperature. I'm going to take a second here to let you think this through. Look at that number that they give to you. It's 10.6 Fahrenheit per what? Per second. Is that what I heard from you, Jasmine?
It's always, it's like,
Well, in this case, it'll help us out because remember, mean value theorem, we're looking at usually the slope. Yeah?
but it's like
That's where you're already asking the next question. When you look at temperature change, does temperature jump from one temperature to the next?
No.
Temperature change very consistently. It can be fast, it can be slow, but it's consistent. It doesn't ever just go from 0 to 100 as a jump. 0 to 100 real quick is still consistent, right?
That's
Mm-hmm. Mm-hmm. See, now here's the thing. I don't know if the temperature while it's boiling, if it gets hot really fast and then it like slows down. I don't know if it gets hot, then cold, then hot again, right? I don't know if the stove's being turned on and off. But I do know at the start it's 0 degrees and at the end it's 212 degrees. And I know it has to get there smoothly. So first things first, I know that the temperature change is something that's continuous. Would you agree?
Yeah.
It has to move continuously. Not only that, temperature doesn't go in a cusp motion. It doesn't do like a rapid change to a rapid drop. It also doesn't go as a corner. There's no absolute values in temperature change. So not only is it continuous, temperature change is also what? Yes. Why is that important?
Because it's MVT.
Yes. Differentiable. So since it's continuous and differentiable, there's some rate at which the temperature is changing, or in other words, the derivative of the temperature should equal to the slope of the secant line right here. How do I calculate the slope? I only have this point and this point. How do I calculate the slope? Exactly. So 212 minus 0 over 20 minus 0. What's that equal to? 10 point what?
Oh.
Isn't that weird? Why am I pointing out to be weird?
It's the same number.
It's the same number as what they're asking about.
Oh.
So, why can they say that at some point the mercury is rising at exactly 10.6? By what?
By number.
By, what's this thing called? What are we using? The mean value theorem guarantees it. Remember, that's the whole point. The mean value theorem guarantees that this exists as long as the function is what? It's differentiable and continuous, right? Since I proved that it's continuous and it is differentiable, the mean value theorem states that the slope, or the rate at which the temperature is changing, should be equal to, at some point, the slope of the secant line, right? And it's guaranteed.
So, where it says the derivative of temperature, you put rises on line. Where did you get the 2 on the top?
The two,
Oh, it's 2, 1, 2. Okay.
yeah, sorry.
I thought it was
212, sorry, that's this one right here. So remember, get that in your mind when you're doing these mean value theorems. The idea is proving existence, right? So even though this word problem seems complicated, it's not that complicated. It's even less complicated than number 6, right? It's just the idea that you understand, like, hey, temperature moves continuously. It's differentiable. Therefore, at some point in the middle, the rate at which it's changing, derivative, should be equal to the slope of the tangent lines. That's it. You feel okay? No, yeah. So.
Never get it for sure, yes, from
more
this
for
class.
like fun.
for fun. Yeah.
Yeah, that's called homework. That's these problems right here. So you can do after 12, you can do number 18. 18 asks you to find the, oh, that's the next part we got to talk about.
Oh yeah, let's talk about
Another one.
Whoop. Let's go into our notes. This will be the last part of it.
Number 18.
No, we're going to our notes. So, notes. So let's go over here. So, we're going to do one new topic onto this mean value theorem, or 2 new topics actually. First topic after the mean value theorem is this topic right here, is Rolle's theorem. Rolle's theorem is a special case of the mean value theorem. It's neat. This guy actually got a theorem named after himself for something very, very simple. This is a real person, by the way, Rolle. This is not on your paper notes anymore. This is just going to be regular notes. Yeah, you just write in your notes. There's 3 conditions for the Rolle's theorem. You ready?
Is it still 4.2?
Yeah. First one is the function needs to be continuous on the interval from A to B. Yep. Just continue on another sheet. The function, it has not. It's like a special case of the MVT, right? It's the special case of the mean value theorem. So let's go with this part right here. The function needs to be continuous on A and B, closed interval. Second thing, the function,
So now we're doing calcs.
yes, needs to be differentiable on A to B.
This is still 4.2, right?
Yeah. Rolle's theorem, like I said, it's still connected to the mean value theorem, but it's a special case. Special case. Rolle's theorem, special case in that case. So do you,
be a time where like, oh wait, yes there was. Sorry, I answered my own question.
awesome. So this is just a couple theorems that kind of like build off of the mean value theorem, like the idea of existence, right? Rolle's theorem is an interesting one. Do you look at if you look at the first two conditions, it's exactly the same as the mean value theorem. Do you see it? Continuous and differentiable. The last part of Rolle's theorem is this. The endpoint values, f of A, is going to be equal to f of B. If the endpoints are equal to each other in the function, like if it's going from 0 to 3 and the function at 0 is equal to the function at 3, an interesting thing happens. At some point, the derivative should be equal to 0. Guaranteed that it'll equal to 0 for some value of C that is in A to B. So Rolle's theorem is a special case of the mean value theorem. If you think about it, right, all the mean value theorem was we would calculate the slope of the secant line and look for a tangent line that was parallel to that. Do you remember that? That the secant line is always that like diagonal looking line, right? I'm saying this. If you come across a problem where the functions at the endpoints equal to each other, it'll look something like this. Put it over here. Let's say I have a function that is going from A to B, and it looks something like this. It goes up, down, and then matches back up to here. If f of A is equal to f of B, which is this part right here, what's the slope of this secant line? If f of A is equal to f of B, what's the slope of the secant line equal to? 0. Which means that there should be a tangent line that's also parallel to this if it's continuous and differentiable. Which means that the slope of the tangent line should be equal to what?
0.
Do you see it? You're guaranteed to have a point where it's equal to 0. And in this case, we have 2. That's all Rolle's theorem is. Rolle's theorem is a special case. If f of A equals to f of B, the secant line is 0. That's all it is. The secant line is going to be equal to 0. Therefore, the derivative should be equal to 0 at some point.
So everything's
The derivative should be equal to 0, yes. You don't actually have to memorize this, because if you actually went through and did a problem that came out like this, you would actually see that when you calculated the slope of your secant line would be equal to 0 over something, which is just equal to 0. So when you go back to do your problem, you'll get the derivative equals to 0, and you just solve it algebraically. That's actually the main part of what we do in calculus. We always try to find out where that occurs.
Isn't that the same thing that we did here?
Mm-hmm. Yeah, that's why I always hated this guy. This guy got the easiest thing that he found and got it named after him. It's exactly what we did earlier, but he's got his name attached to this.
It could have been Naki's
It
theorem.
could have. If I was only born like 2,000 years, no, 600 years ago.
How do you go from 2,000 to 600?
I went in the 2000s, and it was like before. And then I found out it was like in the 1000 something, like 1400s. So like maybe 1400
How
ago.
long has calculus?
Not that long. Calculus is a more relatively new math, but even though when I say relatively new, it's like about 400 years, 300, 400 years.
So new.
It's considered modern math.
Yeah.
What?
Yeah.
Because compared to the other like basic elements of math, those were created like centuries ago.
5,000 years ago for some of them.
I thought you
Algebra.
said something else at first.
You know, algebra is considered like one of the oldest things of math, and like not the oldest, but it's like a repetitive math that's been around since like 5000 BC.
And it's still relevant.
The number 0, on the other hand, hasn't been around as long.
Imagine
What?
being that relevant for that long.
Wait,
All right.
Damn.
wait, nothing real quick.
Mm-hmm.
So when it says f of a equals f of b, they just equal each other at the same point where the slope is parallel? You know, where the tangent is parallel?
Yeah. So here, what Rolle's theorem is stating is this. Picture a function. Let's say I have an easy function. Let's say it was just x squared. That's a nice parabola, right? Would you agree? Let's zoom out so we can see it. Here's my parabola, right? Let's take off that tangent line right there. And let's say I was doing it from negative 2 to 2. So what I'm saying is for Rolle's theorem, it's still the mean value theorem. But the secant line for Rolle's theorem is always going to be flat. If f of a equals to f of b, you see how f of a looks at f of b right there? If they equal to each other, then the tangent line that's parallel to that is also going to equal to 0, which we already know because that's what the mean value theorem states. It's going to equal to that. But since f of a equals f of b, the slope is 0. Therefore, the derivative will equal to 0. Check this out. You could do this anywhere. I could go to negative 3 and positive 3. F of b equals to f of a. What's the slope of that secant line? Yeah, you can even look at my fancy calculation right here. Look. 0. See it? So Rolle's theorem is just that. If the secant line slope is 0, then the derivative at some point has to equal to 0, which it does. Do you see it? Right down there. Parallel to that.
I have a question, and it might not make sense at all.
Okay?
But if it's like that, then wouldn't the wait? How'd you write it? Let me make sure I have it written down correctly first. Yeah, if it's like that, then wouldn't that mean that like they both equal, like f of a and f of b both equal 3? And if it's like on opposite sides, wouldn't it be the absolute value of it?
You're overthinking it. So. In this problem, look at this example. A is negative 3. B is positive 3. But f of a is not 3. F of a, in this problem, is 9. Do you see it?
Oh, okay.
It's 9, right? Because, bro, I'm making a, there you go. Does that make sense? It's 9 because the function is x squared, right? So negative 3 squared is 9. So f of negative 3, or f of a, is 9. F of 3, which is b, is also 9.
Okay.
So that's how they equal. That's how Rolle's theorem works. Okay? So that's Rolle's theorem. Man, I didn't get enough time to get into this last theorem. I don't actually know if you'll be able to do this, but I need you to do this part on your own. In your notes somewhere, can you write down this word? The extreme value theorem. Extreme value theorem. I want you to put down this definition of this somewhere in your notes, and I want you to look it up. The extreme value theorem. Can you guys look up what the definition of that is? I got 2 minutes, but I'm going to stop it there. It's actually a fun one for you to look up. It's not that hard. It's an interesting one. It doesn't have to deal with it has to deal with existence. It's still an idea of existence, but we're not looking at derivatives existence this time. We're looking at extreme values.
So we have to do
Yeah,
those
it
on our
states
own.
that it
A little bit. Just get that equation in there. All right, I'm gonna stop it here, and that's it for today.